Yeah, so do I need to stand in front of this?
Depends on how loud you can talk.
Okay, I can scream.
Okay, good afternoon. Glad to see those of you who are here. So today we have for our speaker is Meg Smith. She's one of our sort of more advanced graduate students in the Earth and Space Science Department. She got her bachelor's degree in meteorology from Penn State, and she actually just gave a talk in Seattle Town Hall on Monday. So she's giving lots of talks today, or this week. And she'll be talking today about Mars' atmosphere and also talking about a little bit, I would suspect, about an upcoming mission to Mars called Mars Maven.
Yep. Thanks, Erica. All right, so I'm not going to use a mic. Can you guys all hear me? Yeah. Great. So as Erica said, I'm Meg Smith, and I am a graduate student in this department in Earth and Space Sciences, and I'm also a member of the astrobiology program, which is a group of graduate students that work on anything ranging from the origin of life to the evolution of life to like extraterrestrial life. So to begin with today, I wanted to show you guys a picture of a planet you know well, Earth, and maybe one you don't know so well, Mars. And you'll notice just by looking at these that they look extremely different. And you can tell there's tons of diversity on planet Earth. We've got oceans, continents. We can even see an atmosphere here. We see the clouds, and it tells us about the atmospheric circulation. Now, Mars there doesn't quite look so interesting, at least from this perspective. In fact, you can't even tell there's much of an atmosphere there, and it looks kind of dead. And if we zoom in a bit more, well, it kind of still looks the same, right? But actually, luckily through spacecraft and rovers on the surface, we've developed a more complex picture of Mars over the past few decades, and we've learned a lot about the atmosphere. So the first thing I want to show you here is actually a video that we've attained from a satellite that will show you some clouds on Mars. So this doesn't have any sound, it's just, we'll see it go by here. So I think this is pretty neat, and this almost looks a little more Earth-like in a way. So how many of you guys have even seen something like that before on Mars, from Mars? A few of you? Okay, great. All right. I'll start this up again. All right, now this is a bit tangential to the atmosphere, but I wanted to show you guys also just some pictures from the surface to show you what an interesting place Mars is and get you really excited. This here is a crater on Mars. It's really well preserved. It's over 100 million years old, and this was explored by one of the Mars exploration rovers back in the mid-2000s. This here is Olympus Mons. This is the largest volcano in the solar system. It's 3 times higher than Mount Everest, and it's also, its footprint there is as big as the entire state of Washington. That's pretty crazy. And then we've got more interesting features. This here is Valles Marineris, and it's a just massive canyon, 4 times as deep as the Grand Canyon. And if you were to put it on Earth, it would stretch almost the entire length of the continental United States. And then to get back into the atmosphere a little bit, we've seen some other interesting things, and I hope you can sort of see these. Maybe I need to put the lights down. Ooh. Well, that didn't help at all. Okay, so these are dust devils moving across the surface of Mars. These are pictures taken by the Mars exploration rovers, once again. And the cool thing about these is that they're actually, they're huge. They're 12 miles tall. And to give you an appreciation, that's 4 times as tall as Mount Rainier. So like, I like to think like, what if I had woken up one morning and looked outside my window and seen a dust devil 4 times as high as Mount Rainier moving by? That's a pretty alien and crazy world. at some other stuff here, we have some evidence just by looking at the surface of Mars that it's a really dry place. These are sand dunes, and they're actually covered with carbon dioxide and water ice. That's most of what you see there. But those dark splotches, that's where the carbon dioxide ice is sublimating away into the atmosphere. So if you've ever played with dry ice or seen dry ice, this is what's happening on Mars, but at a larger scale. And then we see more evidence of dry Mars when you zoom in a bit more. These are marks left by NASA's Phoenix lander. It had a little shovel and it dug, kind of scratched the surface of Mars. And right below you'll see those white little patch up there. It exposed water ice right below the surface. And we could actually see that sublimate away into the atmosphere. Okay. So in my opinion, probably one of the most interesting things about Mars, and I hope this comes through here, is that we've seen some features that we just didn't expect to be there at all in our past 50 years of exploration. On your left there is a picture taken from a satellite of a dried up river valley on Mars. And if you don't believe me that it was a river valley, then just look over here to the right. This is a picture from Earth. It's actually in the Ukraine, and you can tell that the morphology, it just looks very similar. But the difference is that this river valley on the left here was formed around 3 billion years ago, or maybe even a bit before that. And if you recall, Earth and Mars are around 4.5 billion years old. So this is way back towards the infancy of Mars. So the fact that water flowed on Mars a long time ago has interested a lot of scientists. And there are quite a few people, including my undergraduate advisor who I worked with at Penn State, that thinks that Mars used to look like this. And I don't know about you, but if I had just come into this classroom right in the back right now, I thought this was Earth. So okay, maybe Mars did look like this. So how in the world, or how in Mars, whatever you want to say, how did it get from here to here? And that's a question of atmospheric evolution. So that's what I'm going to mainly talk about from now on. And here we go. So, all right. So the first question then is, what is here? What is now? Like, what is that atmosphere made of on Mars? And what's it like on Mars? For that, we need to define two things: the atmospheric composition and the climate. The atmospheric composition, you've probably heard of this, it's just what gases the atmosphere is made of. And the climate, for the purpose of this talk, is just going to be the surface pressure and the temperature on Mars. So what's it like today? Well, here's actually three, but just one pie chart at the top with an inset and then a pie chart at the bottom showing you the composition of Earth and Mars' atmosphere. So if you can just shout out what atmosphere is at the top there. I got one, that's Mars. Awesome. That is Mars. And one thing, and down here is Earth. And the thing you'll notice right away is that Mars is quite different. Most of its atmosphere is made of carbon dioxide, whereas on Earth, most of the atmosphere is made of nitrogen. And then you've got a bit of other gases, scattered around there, but for the most part, that's what's happening. So, all right, you've got the picture here. And I should say, these measurements of the atmosphere of Mars have been made over the past few decades. And this pie chart here, I think, was mostly made from measurements from the Viking missions. So those were two landers and orbiters that went to Mars back in the 1970s. They made these measurements. But an even cooler thing is that just recently, the newest rover on Mars, the Mars Science Laboratory, which I think you guys heard about last week, that made yet another measurement of the Martian atmosphere. And for the most part, it confirmed what we thought. The atmosphere is mostly made of carbon dioxide. There's some argon. Argon's a noble gas. and then nitrogen, oxygen, and some carbon monoxide. So I think an even cooler thing about this is it means that we have the technology to take instruments like the Mars Science Laboratory, take it to all sorts of planets if we had the money, and measure the atmosphere. All right, so in terms of Mars climate, what's it like there? I just wanted to give you guys a picture. It's definitely an alien planet. The surface pressure is around 6 millibars. So to experience that surface pressure, that pressure on Earth, you'd have to go to an altitude above where airlines fly. The mean surface temperature is around -70 degrees Fahrenheit, and that's similar to the temperatures that people experience at the South Pole in Antarctica. And like I said before, it's really, really dry. So generally, it's a very inhospitable place for life to be. So a question you might have at this point is, all right, we've got Earth right here, and we've got Mars just a little bit behind us, a little bit away from the sun. So how did these planets become so different? And I'm kind of giving you the punchline of the talk here, but there's two main reasons. And the first is that Mars's atmosphere has been lost into space over time. And the second, that we'll get to later in the talk, is the fact that Mars's prime greenhouse gas and overall gas, carbon dioxide, hasn't been recycled over time. So it's just been accumulating in the atmosphere and swept away into space. So to understand the story of loss, atmospheric loss, we need to ask ourselves really three questions. First, where did the atmosphere come from? Second, how did its atmospheric composition evolve? And third, how did its climate evolve? So let's start with this first one here. So back in the beginning, once upon a time, this is the solar nebula here. And you'll see that there's some little globs going around. And those are what we call planetesimals. They're the beginnings of planets, and they're forming, and they're going around, revolving around the sun. And what you might think is that where they get their atmosphere is from this kind of gassy pool around the sun. And I sort of like to think of it like the sun's like bath juices. Like it's just coming off the sun, and it's got pretty much the same composition as the sun. So like I said, maybe you would expect these little planets to be snowballing and picking up the gases from the solar nebula. But actually, we have evidence that the primary atmosphere of both Mars and Earth wasn't accumulated in this way. And our evidence here are from our noble gases. So I mentioned that argon was a noble gas earlier. Noble gases, they're just very unreactive. And if you think about the periodic table in your head, they're on the far right end. So those noble gases, they were in the sun's kind of bath juice here. And if a planet moving through, snowballing through that nebula had picked up noble gases, because they're unreactive, they should have stuck around basically forever until now. But what we see, if you look at the graph on the left here, and I'll circle, these are the noble gases. And you'll notice that there are dips on this graph. And what that means is that, this one is for the Earth, this plot here, but it's also the same for Mars. This means that on both Earth and Mars, we're missing a lot of noble gases that should have been there if we had accumulated them from the solar nebula. So where did these gases come from? Well, we think the answer is that they came from other sources like comets and asteroids. If you think about the early solar system, it was a pretty chaotic place. So there's just things zipping around everywhere. And those comets and asteroids, they had solids on them, like water ice and hydrocarbons. And once they slammed into Mars and Earth, that's where it got its gases from. And then you might ask, okay, so if they were snowballing around and did collect some of those solar nebula gases, where did they go? And the answer, we think, is that the very early sun was active, and it probably just kind of stripped the atmosphere away. So yeah, those noble gases are like the cash money here. They're really interesting, and we can learn about something that happened such a long time ago. All right, so kind of a caveat of the fact that we're having the early solar system is very chaotic, is that not only do you have comets and asteroids slamming into the planets and delivering gases, but they're also heating up those atmospheres. And they're essentially taking all of those solids, heating them up really hot, and putting them into the atmosphere, so that we accumulated on Earth and Mars steam atmospheres. If you can think about that, it's just kind of mind-boggling to think about an atmosphere full of steam. But obviously, that's not the case what we see on Earth and Mars today. So where did those atmospheres go? And how did the early atmosphere evolve? Well, to look at that, I'm going to focus in on two processes. The first one is called Hydrodynamic Escape. And this happens, so I told you before, we had our atmosphere full of steam. And by steam, I mean water vapor. So a bunch of hydrogen and a bunch of oxygen. And in the early solar system, the sun had really active ultraviolet radiation. So there's all this water up there, and the sun is emitting these high energy photons that come into Mars and split that water apart. And now all of a sudden, in this orange layer here, you've got a bunch of hydrogen, and it's really energetic, so energetic, in fact, that can actually exceed the escape velocity of the planet. And so in this process here, you have a bunch of hydrogen that's just kind of en masse leaving the atmosphere and dragging with it a bunch of other atoms and molecules in the atmosphere. Now, this does not happen today, but we think it was a very important loss process in the early Martian history. Now, around this time when this was happening, when we had our kind of mass escape from Mars, it was also a time when there were lots of different things happening in the solar system. One is called the heavy bombardment. Has anybody heard of this? Just show of hands. Okay, a couple of you. So this is right around when the planets are still forming, and there's also a period after this or kind of at the tail end of this, called the late heavy bombardment. And this is a really interesting period because we think that the orbits of Uranus and Neptune actually switched places. I mean, that's crazy to think about. And when that happened, because everything was being disturbed, we think that there were a lot of asteroids that were sent in to the inner solar system and started bombarding a lot of the planets. And so if something is bombarding a planet the size of a giant asteroid, it's carrying with it a lot of energy. And that energy is put into a lot of different, you should read the caption on this, by the way. I expect a couple laughs there. Yeah. So with this, the energy that the asteroids and comets are bringing, they can actually just blow off the atmosphere. We think this was probably a very important process early on. Not so much today, and maybe during the time of the dinosaurs, there was a little bit of atmosphere that went off into space, but a long time ago is very important. So we can do some estimates, and some people have tried to understand exactly how much of Mars's atmosphere was lost just by impacts. So I'll walk you through this here, just a second. So first of all, we actually don't have a great way to say how much atmosphere Mars started with. But we can do a little estimate, and we can say that if Venus has around 90 bars of carbon dioxide, Earth has 60 bars of carbon dioxide, And before you say wait, not all of that is in the atmosphere. In fact, a very little amount is. Most of it is in our crust and mantle. But if we consider these, and we consider the mass of the two planets, if we scale that to Mars, we would expect that Mars started with 60 bars of carbon dioxide. Or sorry, 6 bars of carbon dioxide. And remember today I told you that it only has 6 millibars. So people did some calculations, and they figured out that if there were a bunch of comets and asteroids zooming around early on, that Mars would lose around 99% of its atmosphere during the first part of its history, right up until the end of the heavy bombardment. And then after that point, Mars lost even more of its atmosphere. And to get into that, I need to tell you about a couple more escape processes. So this hydrodynamic escape and the impact erosion, those were very early on. But Mars and Earth actually are still continuing to lose their atmosphere today. One kind of escape is called Jeans escape, and this is named after an English astronomer who discovered this process. But you can think of this like sort of like a planetary tea kettle. So very high up in the atmosphere, we have on both Earth and Mars, there's hydrogen that's very energetic and very hot. And that can just, with the sun's heating, evaporate away into space. So this is sort of like a very slow leak, but it's been happening over the history of the solar system. Another interesting process that happens just on Mars, because Mars doesn't have a protective magnetic field, this is called sputtering. And sputtering is created because we have a sun that is giving off energetic particles and radiation, and that's creating something called the solar wind. So you can think of sputtering sort of like it's a giant like broomstick. You have the solar wind coming off, and it's just brushing off the atmosphere of Mars. And I'm going to show you a video in a couple minutes to explain a little more about sputtering. All right, and our last kind of escape that I'm going to go over now is something called photochemical escape. And this is when you have molecules in the atmosphere that just slowly drift up to the very top, and they're ionized. That means that they lose an electron. And they're all floating around. Now we have molecules and atoms and electrons. And when they recombine with each other, this is like a very energetic process. Energy is released, and these molecules and these atoms have enough energy now to escape the gravity of Mars. So I like to think of them as little rocket ships going away. So these processes, photochemical escape and sputtering and Jeans escape, are acting slowly over long periods of time. So as Erica mentioned earlier, there's actually a mission going to Mars later this year called MAVEN. And MAVEN is really awesome because it's the first orbiter to go to Mars to study specifically the atmosphere. And we're hoping that it can tell us some more things about the evolution. And so now I'm going to show you a short video. Let's see if this works. So this is explaining a little bit about MAVEN and about sputtering.
When you take a look at Mars, you probably wouldn't think that it looks like a very nice place to live. It's dry, it's dusty, and there's practically no atmosphere. But some scientists think that Mars may have once looked like a much nicer place to live, with a thicker atmosphere, cloudy skies, and possibly even liquid water flowing over the surface. So how do you go from something like this to something like this? NASA's MAVEN spacecraft will give us a clearer idea of how Mars lost its atmosphere, and scientists think that several processes have had an impact. One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. In our solar system, the sun constantly emits high-energy photons. When one of these photons enters the atmosphere of a planet, it can crash into a molecule, knocking loose an electron and turning it into an ion. Ions by themselves don't do much, but when a magnetic field is nearby, they'll spin around the field, spiraling in the field's direction. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. The part of the field that just grazes the planet can easily pick up a bunch of ions and launch them out into space. If the field happens to be in just the right place, however, it might pick up ions and fling them right back into the atmosphere at up to 1,000 kilometers per second. The ions can then crash into other molecules and fling atoms everywhere like a cue ball in a game of pool. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. And over billions of years, this could have caused quite a bit of change, especially since the solar wind may have been more intense early in our solar system's history. Scientists think that all of this may have caused Mars to gradually transform from what may have been a very nice place to live into the dry, dusty world we know today. And Maven will study this process and tell us how it really works.
So that's actually all I'm going to tell you about Maven, but I encourage you to go look up more about Maven. And something that I just found out the other day is that aboard Maven, they're actually sending a DVD, and anyone in the United States or maybe in the world can send their name, enter their name on a website, and it'll go on that DVD. So if you're into Mars exploration, I encourage you to go Google that, put your name on a DVD for Maven. Kind of fun. All right, so to wrap up this part of the talk, we were talking about the loss of the atmosphere. We had a very chaotic early period in Martian history, and around 99% of the atmosphere just lost into space. And then after that, you had another 90% of the remaining 1% that was lost. And this happened mostly later on through sputtering and photochemical escape. And just to put that and show you the whole picture there, we got 6 millibars of carbon dioxide in the atmosphere at the end, 60 right after the late heavy bombardment, and probably around 6 bars before. All right, so on to a little more of the mysterious part. How did the climate on Mars evolve? And remember, climate, I was talking mostly about the pressure, the pressure we already covered, but the surface temperature on Mars. First, to understand that, I just want to show you how a planet attains its temperature. And this is called planetary energy balance. So this here is sort of like a naked planet. You have radiation coming in from the sun that heats the planet, and then the planet gives off energy. So it's sort of like sunbathing. You're laying in the sun, you get the energy from the sun, and then you radiate that everywhere and sweat and get nasty. But anyway, most of us know that this isn't the whole story about what makes a planet warm. In fact, we've kind of heard a lot about this recently, and that's the greenhouse effect. And I consider that like a planet's clothes. It's extra layers on the planet that's keeping it warm. And those extra layers are gases. And what those gases are doing is that they're absorbing radiation that's coming off of the planet, and then they're re-radiating it both down and up. And the net effect is that you get a warmer planet. So here I've just shown you, broken down some of Earth's greenhouse and where that comes from. It comes from mostly water vapor, but also a little bit of carbon dioxide. Carbon dioxide, as I said before, is the main gas on Mars. So this is where the main greenhouse effect comes from on Mars. But the greenhouse effect is still very small. Remember, I told you that the temperature on Mars is somewhere around -70 degrees Fahrenheit. So let's focus in on this carbon dioxide molecule. It's a really interesting molecule, and that's because on Earth, it's actually recycled. It doesn't just live in the atmosphere all the time, a molecule of carbon dioxide. It goes around, it comes onto the Earth's surface, it's subducted through plate tectonics, and then it ends up in volcanoes coming out again. So I'm sorry that this is a terrible image here, but it's just meant to show you the cycle that a molecule of carbon dioxide makes on Earth. And it's really dependent on having two processes working. Like I said, plate tectonics, so that that molecule can be subducted, and volcanism, so the molecule can come out again. But the problem with Mars is that we don't have these two processes. I showed you that giant volcano, Olympus Mons, but it's dead, just like all the other volcanoes on Mars. And there's also no plate tectonics. So what that ends up leading to is carbon dioxide only being able to live in the atmosphere and then being exposed to all those lost processes we talked about. So it's not a very great greenhouse effect then. Not a great way to get a greenhouse effect if you're losing all your greenhouse gases. Now what about early in Mars history? I told you Mars might have looked like this, but actually we have no idea how it would look like this. And that's because the greenhouse effect story gets even worse early in Mars's history. So you notice our bright, sunny, sun here today? Well, a long time ago, it wasn't so bright. And it emitted less energy, and therefore both Earth and Mars couldn't get as warm. So it becomes a mystery how Mars might have looked like this. So over the past, I'd say like 30 years, people have looked at what greenhouse gases could have existed in the past Martian atmosphere and what it looked like. So the first thing that people investigated was maybe there was more carbon dioxide in the past Martian atmosphere. Maybe if you just, for some reason, there was 6 or 10 bars of carbon dioxide, bunches and bunches of greenhouse gases, the planet could have been warm. But there were several problems with this. First, when you have a lot of carbon dioxide, you actually create clouds that are made of carbon dioxide. And this prevents the surface from warming. But then wait, so this research field kind of evolved, and then people later started to think maybe these carbon dioxide clouds could have been sort of like disco balls, like scattering radiation everywhere, and maybe that could have warmed the surface of Mars. But probably not, once again. So if this had been the case, then Mars' atmosphere would have warmed up, and then all those clouds would have evaporated away. So although a lot of people think carbon dioxide could have warmed the early atmosphere of Mars, we're just not sure. Now, how about different greenhouse gases? How about, for example, sulfur greenhouse gases? So how many of you guys have heard of sulfur dioxide? Yeah, a good amount. So sulfur dioxide comes out of volcanoes. So maybe this could have warmed early Mars. But no, of course, another problem. And this is actually something that I worked on when I was an undergrad. I did some computer modeling to look at the effect of sulfur dioxide in the atmosphere of Mars. And as it turns out, when you have a lot of sulfur dioxide in an atmosphere, you start to form little particles. And those particles, they grow and they form smogs. And a smog cools a planet because it means that the solar radiation that's trying to get in is reflected away. Okay, so we've gone through our carbon dioxide and our sulfur. What about other gases? Maybe there could have been methane on early Mars. Have you guys all heard where a lot of the methane on Earth comes from? Yes, that's cow burps. And that's because cows have little critters in their stomachs that make methane. So maybe this could have been the case on Mars, but that means that we would have to imply that there was life on Mars, and we don't know that for sure. All right, so there's actually a whole other group of researchers that think that Mars wasn't permanently warm at all in the beginning. In fact, they think back to what I said earlier about the impacts being really energetic and heating an atmosphere. And these group of researchers think that Mars was just warmed up temporarily by asteroids and comets impacting the surface, heating it up, and expelling water into the atmosphere. And they've done some modeling to see that just with impacts, you could vaporize around 100 meters of water into Mars' atmosphere that would then fall back down. So perhaps this is a possibility. All right, how about a related question? I implied that maybe methane could have warmed early Mars, but that might have needed life. So was there life ever on Mars? And this is a question that I'm really interested in, and it's a really hard question to tackle. Like I said, it's clear that Mars wasn't always the way it is now, but was there ever life? And how do we address that question? Well, a good way to do that is to think about very early life on Mars and what that or on Earth and what that required. Very early life on Earth was not like you and I. It didn't breathe in oxygen. It actually breathed in a lot of gases that are called reduced gases, like hydrogen and methane. So could we ever find out if these gases were on early Mars? Well, that's actually part of my research that I'm doing here at the University of Washington. And I'm attacking it from a very kind of quirky perspective. So I'm going to try to explain that to you now. So my research we're trying to use a strange salt that was discovered on the surface of Mars to learn things about the past atmosphere. So here's our salt on the surface. It's called perchlorate, and it was discovered in 2008 by NASA's Phoenix lander. And what we know from Earth is that the salt actually forms in the atmosphere. So I know that sounds a little strange, but just bear with me here. So you have our salt forming in the atmosphere, and what goes into this salt is oxygen gas and chlorine gas. Another way to think of it is sort of like water vapor condensing and going into a snowflake. So as it turns out, this oxygen gas can actually be a key to telling us about some of those reduced gases, those hydrogen and methane gases. And that's because in an atmosphere, oxygen gas and methane and hydrogen are constantly fighting each other and destroying each other. So if there was a lot of hydrogen and methane around on early Mars, that means there should be very little oxygen on early Mars. And if there's very little oxygen on early Mars, that means that we should probably see very little of this salt. So to give you a picture of that, on the top there is what we see on Mars today. And I've included a little pie chart to show you that there is quite a bit of oxygen on Mars. We see this perchlorate pretty much everywhere. And so my advisor and I thought maybe if we go and look at a place on Mars that's very old, a very old surface, we'll see very little of this salt if there was a lot of these reduced gases around. So I went about trying to answer this question, and the way I did this was by running a computer model to see if the salt actually forms this way on Mars. Like I said, we know it forms this way on Earth in the atmosphere, but does it form that way on Mars? So here's me looking really frustrated running my computer model today. And as it turns out, what I've found out over the past couple years is that the salt doesn't form this way on Mars. So unfortunately, the lesson for this little story here is that sometimes science doesn't quite work the way you expect it to. So although we haven't learned about these past gases in the Martian atmosphere, we've made a step forward just to say that maybe this isn't the right way to learn about the past atmosphere of Mars. All right, so to wrap up here, I just wanted to give you another one of those perspectives of the evolution of the Martian atmosphere. Most of it was lost in the very beginning, and then from there, we had more and more loss. And as Benjamin Franklin said, a small leak can sink a great ship. So this is the way that I see Mars. Might have started great, but over time, its atmosphere leaked away into space, and now it's kind of puny. So thank you, that's it. I'll take any questions from you guys.
Thank our speaker, please.
Yes?
Is Earth safe from sputtering because of its magnetic field?
Yes, yes. So for the most part, there are actually other ways that atmospheres can be lost when you have a magnetic field, and Earth experiences those processes, but Earth doesn't experience the sputtering because it's got its protective shield. Yeah.
How does perchlorate form?
Good question. We're trying to figure that out, actually, and we think that it might not form in the atmosphere, and that it might be some materials on the surface that are being irradiated and then chemical reactions are producing the perchlorate. So perchlorate is produced in other ways that we know of, but we just thought this one would be a really cool way if it was on Mars. Yeah.